Okay, let's start for the lecture for this week. So thus far we have looked at a few different examples of finite element formulation. So if you recall, we started with looking at 1D problems, and in 1D problems we looked at, first of all, we looked at 1D uniaxial loading. Then we moved on to 1D beam bending. Then we looked at 2D problems, and in 2D problems we started with the problem with a scalar variable. So that was looking at heat conductance, where our essential variable, the temperature, was a scalar variable. So now what we want to do is actually move on to looking at 2D problems where our essential variable is a vector. And the example that we are going to consider is that of linear elasticity, right? So the only thing that's different from the scalar case is that for a vector variable, we essentially have to look at the different components in a given Cartesian coordinate system. So for example, if we are looking at a 2D problem, and the example we are using is of linear elasticity, then our essential variable is displacement. And you all recall that displacement is actually a vector. And in 2D, that means that it has two components in the respective basis direction. So that's the main difference from our scalar case, and that's what we need to take into account. The rest of the finite element formulation follows exactly the same procedure. So for linear elasticity, we need to set some sort of ground rules or some fundamental equations, and for that we need to go back to looking at some of our continuum mechanics principles to essentially derive our strong form for the for linear elasticity as we've done before. So first of all, we will start off by looking at how this displacement vector relates to the strains, and then how those strains relate to stresses in order to set up our strong form. So, so the strain displacement relationship essentially we can derive using kinematics. Kinematics is looking at how a body is deforming in a coordinate system, let's say, or in space, independent of what forces are being applied to it. So that is, we're just looking at the deformations and the movement of the body, so to speak. So for this, you may recall that we need to first start off by defining our displacement vector. So in this case, as I said, we have our we are looking at a problem in 2D. So we have two components of the displacement vector in the respective x and y directions. So this is how I'm going to represent my displacement vector with the ux and uy respective coordinates. Now if you're the linear elasticity problem that we are looking at in this course is going to be based on the small strain assumption. That is, we are looking at small deformations such that we are then essentially interested in a very particular type of strain, which is our infinitesimal strains, which we normally represent with the symbol epsilon. Now this small strain epsilon has a number of components. So of course it has, which can be essentially divided into two types of strain. So one is the normal strain and the other is the shear strain, if you all recall from your undergraduate courses. So these normal strains comprise of the normal strain in the x direction and the normal strain in the y direction, which are respectively just measures of the extensions in the x and y directions. Whereas the engineering shear strain that we have, represented by gamma, it is a measure of the change in angle from 90 degrees if we started off with a square infinitesimal area element. So I'll go through these one by one in just a second. So for the normal strains, we have epsilon xx and epsilon yy. So if we have our basis directions x and y like so, and we are looking at an infinitesimal element, such as the one shown here, a square element, then the normal strain in the x direction is basically just the extension in the x direction divided by the original length in that direction. That is, it is this change in the x line segment divided by its original length. So it could be written in terms of this. So del ux with respect to del x, where ux of course is our displacement of, in the x direction. Similarly, the normal strain in the y direction is given by the displacement in the y direction, del uy, divided by the original length, so del y. Finally, as I've already mentioned, this engineering shear strain, gamma xy, is basically the change in angle from this 90 degrees. So our original element has a corner angles of 90 degrees, but once the element has sheared, then there is a decrease in the angle, and the shear strain is a measure of this decrease from the 90 degrees. Right. No matter, let's just assume that we already know these expressions. They are derived from continuum mechanics, but we are just going to take it as a given that we already know what the normal strain is and what the shear strain is in terms of the displacement components, right? So given that we know these expressions, then as always for finite element method, it's useful for us to start to represent these in matrix form. So that's exactly what I'm going to do. I'm going to write my small strain tensor epsilon for finite element method. I'm going to write it as a column vector. So I'm going to say epsilon xx, epsilon yy, gamma xy. For those of you who are familiar with continuum mechanics principles, you know that the small strain epsilon is actually a tensor, which means in 2D it is normally represented like so. So it is represented as epsilon is equals to epsilon xx, epsilon xy, epsilon yx, which is the same as epsilon xy, and epsilon yy, right? It's written in tensor format, but as I've just said, in FEM, we are going to write it in vector notation like so. So we're going to write the strain tensor as a vector with our normal strains coming in first and then our engineering shear strain coming in here. Right. Okay. So, so if we are to write it as vector format in terms of our displacement variables, then we need to introduce this new matrix right here. So going from these equations onto this matrix format, then I need to introduce this del operator matrix, which in this case is it's a new del operator for us. Recall this is something else. This is not the standard del operator. It essentially consists of in the first row del by del x and then 0. That's important. And then 0 del by del y. And then in the third row it has del by del y as the first term and then del by del x. So it's something interesting and something new, right? Now we call this del operator as our symmetric gradient operator. So we have defined this new gradient operator basically, and this allows us to very compactly write down our infinitesimal strain vector like so, such that we then have that epsilon is actually equal to this symmetric gradient operator applied on our displacement vector u. Okay, so it is important to note that this del s has these terms within it. Right. You are welcome to expand this out, this matrix multiplication, to check that we are actually getting the same equations for each of our strain terms as our last slide. Okay, right. So this is basically giving us our strain displacement relationship. Now we need to move on to looking at our stresses, and in particular I'm going to start off by looking first at applied tractions. Tractions are forces per unit areas but applied on the boundary of our component, and what stresses those tractions lead to in a body. right? So that's what I'm going to do. In order to do that, I need to look at basically a boundary element, of course, because it's on the boundary that the traction is applied, right? Let me repeat. Traction is a force per unit area, so same units as stresses, but traction is the effect of the external system on the boundary of our component. So it's for example, when I'm standing on top of a platform, I am applying a traction on that surface. Or when I'm rubbing my hands, so to speak, against each other, then each of my hand, one external system is applying tractions on the surface of a hand, let's say, as an example. Right, so looking at a boundary element for my 2D body, recall that my body is represented, or domain is represented by omega, shown right here, and the boundary is represented by gamma. Then looking at this boundary element, I'm going to write down first the areas of this infinitesimal element, assuming that I've taken a unit length and this sine of alpha. Then I can resolve what the components are for the normal vector coming out of the boundary at this infinitesimal point. And then next I'm going to write down the stresses acting on this infinitesimal area. So recall that I've just said that I'm applying traction on the surface. So this is my surface boundary. So I'm applying a traction. I'm going to represent that traction by a T. Now this traction, of course, can have its x and y components. And the whole idea is that because of this traction being applied, there will be internal stresses that are set up within the body. Those internal stresses are, of course, represented by our familiar sigma symbol. So these are, of course, our measures of internal loadings within the body. So sigma we have as sigma xx, sigma yy, and then the shear stresses sigma xy and sigma yx. Now I can look at, basically, by multiplying these stresses with the areas, I will get the forces acting on this infinitesimal element, such that I can consider the force equilibrium of this element, right? So for force equilibrium, I know that my resolution of forces in the x and y direction must both lead to 0. So I've got summation fx is equals to 0. Now, as I said, multiplying the stresses by the areas on which they are acting. So T in the x direction, Tx is only acting on an area of 1. So Tx times 1 must be balanced by this sigma xx and this sigma yx, but sigma xx is acting on an area of sine alpha, hence sigma xx sine alpha, and sigma yx is acting on an area of cos alpha, hence this term right here. So that gives me force equilibrium in the x direction. Similarly, I can find my force equilibrium, or impose my force equilibrium, in the y direction, such that I get this second equation. Now, of course, I think you may have already seen this coming, but you know that I love to write everything down in matrix format for FEM. So I'm going to write this down as well in matrix notation, such that I get this expression right here, which is, using symbols, I can say my traction is represented by the symbol T, and my stress in tensor notation, please note, as we've just discussed, tensor notation, I'm going to represent using the symbol tau. Okay, so just to identify that this tau is my familiar stress tensor in 2D, being multiplied by the normal vector at that boundary, basically, so n. So this is helping us move one step forward, as you will see, and is telling us what the relationship is between our internal stresses and the applied tractions on that body, right? Okay, so from continuum mechanics, there's a name for this, which for FEM we're not really concerned with it, right? So just want to point out that I'm using tau to represent the stress tensor written in tensor notation like so. Okay, so that's already started to lead us towards stresses, and now finally, of course, as we've been doing for uniaxial loading and for beam bending, we want to impose equilibrium within the body. So for that, I'm going to look at my stresses existing within an element in the main bulk of the body. So in this case, if I'm looking at an infinitesimal area element, I of course have my stresses, but these stresses may be changing over the domain, hence why I have del sigma by del x and del sigma by del y terms in there, right? Secondly, also note that I'm assuming that I may have body terms, that is body forces. These are forces, Bx and By are body forces acting per unit area or per unit domain for this particular specimen, right? So now, of course, this entire problem that we're looking at is a statics problem. So there is equilibrium conditions hold true. So I can impose force equilibrium in the x and y direction, and doing that, I can see that leads me to this equation right here for force equilibrium in the x direction, and similarly in the y direction, I get this expression right here. That is that the change in stress must be somehow balanced by the body forces within acting on the element, right? You're welcome to actually write this out properly, noting that the areas are all 1 because I'm considering an infinitesimal area element, or you could look at the areas being, dx being this length and dy being this length. And similarly, you will still get these expressions right here. But I've not gone into too much detail regarding this. Right, now, as always, we could start to convert this into matrix form. And now if you notice that I have to bring in some del operator, so there are partial differentials with respect to x and y, and it turns out that I actually need to introduce the symmetric gradient operator that I've already introduced previously in order to write these two equations in matrix format. So please expand this out, see we get these two equations again, but just jumping directly into it. So we have our del S operator, but look carefully, it is actually the transpose of the del S operator, right? So go back a couple of slides and have a look. So this is the transpose of the symmetric gradient operator being multiplied by the stresses, but the stresses written in vector form, so a column vector form, and hence why I'm going to use a new symbol, which is our sigma symbol, to represent the stresses written in vector format. Okay, so sigma is stresses written in vector format. Similarly, how I had my epsilon as the strains written in the vector format. Recall that I also have this symbol tau, which is my stresses written in tensor format. Sorry, something like this, 2 by 2. 2, 1 here, 1 here, here, and here. Whereas these are vectors. Epsilon and sigma are vectors for FEM. And finally, I also need a vector to represent by my body forces. So this is, I'm going to take as B. So Bx and By are components of that. And that, of course, because of equilibrium, they must sum to 0. So this gives me my equilibrium equation, basically. Perfect. Yes, one just last thing to point out, that the body force is per unit volume or per unit area if you're looking at a 2D problem. Right, okay. So finally, we need to tie all of these up, that is the stresses and the strains, that is the internal loadings with the displacements in the body, by using a constitutive material law. And for a linear elastic material in the small strain regime, that is the Hooke's law. So Hooke's law tells us that the stresses are related to the strains by this equation right here. So sigma is equals to dE, d epsilon, where this d is a matrix containing our material properties. So the way we've represented our sigma and epsilon, our D will be a 3 by 3 matrix, and it depends essentially, it consists of our material properties, but also for our 2D problems, it depends whether we're looking at a plane strain 2D problem or we're looking at a plane stress 2D problem. So just to recap, if in case some of you do not remember from your undergraduate what plane strain and plane stress are, plane strain is the case when we have a specimen which is very thick. So if it's very thick, then we can assume basically that the strains in that particular thick dimension are all zero, right? So that's plane strain, whereas conversely, plane stress is the case when we have very thin specimens such that we can actually assume that the stresses in one particular thin direction are all zero. So that essentially leads us to getting two different expressions for this D matrix, the material property matrix, and for an isotropic material, which means it just needs, it has the same, let's say, Young's modulus or elastic stiffness in all directions, then our D is under plane strain takes this expression right here, as I said, in terms of material parameters, so in terms of E and nu, where E is the Young's modulus of the material and nu is the Poisson's ratio of the material. And under plane stress, it takes this expression right here. Right. So we just need to be careful which particular type of 2D linear elasticity problem we're looking at. Now, to tie all of this up together, what do we have? So we have our equilibrium equation given right here. Next, we know that we have our strain displacement relationship, which we've already considered, and our stress strain relationship, our Hooke's law. So what we can do is that we can substitute all of these in here. That is, first substitute epsilon into the stress strain relationship, and then substituting sigma in our equilibrium equation to get our strong form basically in terms of the displacement essential variable. So this is basically our strong form for 2D linear elasticity, which we can also call planar linear elasticity, because 2D means that we're looking at a problem within just one plane, right? Finally, a strong form also consists of the boundary conditions being applied on our particular specimen. So that would be if we are looking at our body, our domain in the XY coordinate system like so, we can have either our essential boundary conditions, which would be the displacement boundary conditions. So they will be applied on some parts of our boundary, whereas our natural boundary conditions will be our tractions for this particular case. Okay, very important. So our natural boundary conditions are tractions, and they, we say, are being applied on the part of the surface or part of our boundary which is represented by gamma t for traction. Right, so we have our essential boundary condition on gamma u and our natural boundary condition on gamma t. Noting that here we have used our Cauchy stress relationship that we had derived before, which was that the stress the stress arising at the boundary because of an applied traction would be given like so. Okay, so tau was the stress tensor. Perfect. Okay, so as always, our next steps are to convert our strong form into our weak form. So that's what we will start off now. Okay, so I think, yes, just a word of caution. So as you all know, we are looking at a vector field variable. So converting the strong form into the weak form is a little bit more involved. It's not something that's too complicated, but just in the interest of time, because we've done so many of these problems, I will not be going into it in too much detail, and we'll just be briefly passing over this. So in this case, because our essential variable is a vector, so this time around, the weight function that we introduced is also actually a vector. So this time, this is the main thing that needs to be pointed out. That this time we introduce a trial vector function w, which then has respective wx and wy components, and we multiply it to our strong form and integrate over the entire domain as before. Now it's very important to look at this carefully, that there are things which are written in bold script. So W is bold, this del S is bold, sigma is bold, B is bold, everything is bold, even this 0 right here is bold, because we are actually looking at all of these are vectors or tensors. In other words, they are all matrices. Okay? Even the null vector 0 actually consists of two zeros, 0 and 0. And similarly, W consists of Wx and Wy and so on. So you have to be careful that this integral equation actually consists of two equations, one for the x coordinate and one for the y coordinate, when you look at this entire expanded equation, right? But as I said, I'm just going to jump through how we get that. So you're welcome to please go back and look at your textbook to see how the actual conversion from strong to weak form happens. The procedure is exactly the same. That is, we take our the term with a differential in it, we integrate it by parts, and then we apply divergence theorem to it. Okay, the same as what we've been doing before. So we integrate this term by parts and then apply divergence theorem to get our expanded equation essentially. So once I apply my divergence theorem, I convert my domain integrals into my surface integrals, and then noting that I actually do know some of my surface integrals. That is, I know my boundary condition at gamma t. So just substituting that in here. Right. So yes. So do take a look at it in your textbook for more details on this. Nothing that we are unfamiliar with, or try it on your own. That would be even better. Right. Finally, I'm going to introduce actually that so far I've just got it in terms of sigma. So why don't I actually replace sigma using my stress strain relationship and then my strain displacement relationship to convert sigma into my a form in terms of my essential variable. So if I do that, then I know that my sigma is basically d epsilon, where epsilon is equals to del S u. So that gives me my weak form in terms of the essential variable right here. Now, as you can see, that if I had already made my substitution in here for sigma, this strong form was actually a second order partial differential equation for my displacement. Whereas now, by using my trial function, my weight function, and my weak form, I've converted the second order differential into a first order differential, with one differential being in terms of the weight function and one differential in terms of the one differential of the displacement vector, right? So that's basically it, and this is our weak form of our planar elasticity problem. And as before, our aim is using the finite element method to find an approximate solution for this u that is able to satisfy this above equation for all arbitrary, sorry, not for all, sorry, for our arbitrary trial functions w, where the only condition on w is that this w is actually equal to 0, wherever we have our essential boundary condition, that is all on gamma u, right? So for that, if you recall, what we tend to do is then that we discretize our domain and we introduce our approximate fields over that discretized domain. Now, this is of course us converting our weak form into our Galerkin weak form. Now, Galerkin weak form means that we are basically going to use our same interpolating functions, same approximating functions for both my essential variable and my weight function. So hence why I've just got the shape functions n as my approximating functions for u and for w. So just substituting these into my weak form and just seeing what happens slowly. So wherever I have w, I'm going to substitute wh, and wherever I have u, I'm going to substitute in uh. So just done that. Next, I'm going to substitute in what these are. So UH is NA, where A are my nodal degrees of freedom of my discretized domain, and W star are my arbitrary nodal values for the weight function. Right? They're arbitrary. They could take essentially any value, except that they must fulfill overall that W is 0 at the essential boundary, right? But within the domain, they could take any arbitrary value, right? Okay, so substituting those in, I get wherever I have WH, I get the NW star. Wherever I have UH, I get NA. Now starting to play around with just standard matrix manipulation. So I'm going to expand out the transposes. Let's see. So recall this transpose I can expand to be the transpose of the first term, W star, and then the transpose of the second term, so del S N's transpose. And now introducing my familiar B matrix, which consists of the differentials of the shape functions like so. So I'm going to say that B is the del S multiplied by N, and finally noting that my A and W stars are actually constants, so they are the nodal values, so they are constants, so I can take them outside of the integrals. If I do that expansion, all three of these manipulations, then I get these expressions right here, where I have my W star t constant outside on the left hand side of the integral, and my A constant on the right hand side of the integral on this for this term. Whereas on my right hand side, I just get W star t outside. Okay, I'm hoping that this is looking increasingly familiar to all of us. So let's just manipulate it even more to write down this del S n in terms of B, in terms of my B matrix. So if I do that, I can manipulate this one right here as then becoming B transpose dB integrated over the entire domain. Whereas on the right hand side, I just have what I already had. Right. So, yes, what can we do next? Perhaps we can write it slightly more compactly by noting that we could introduce some terms to represent these integrals. So what I'm going to do is that I'm going to represent my integral of bt dB as over the domain as my stiffness matrix K, and representing my right hand side of the previous equation using my force vector or right hand side vector like so, where in my force vector, please note that there are two different terms. One is the domain term, so I'm going to call it my body force vector. Okay, so it just consists of the body force vector being integrated over the entire domain, multiplied by the shape function and then integrated over the entire domain. So it's a body vector term, and then a boundary term which consists of the applied tractions on our particular specimen. So that is going to be my surface forces essentially, right? So using these notations, I can write down my Galerkin weak form more compactly like so. Finally noting that we know that our weight function is arbitrary. So the only way for this to be fulfilled is if our Ka is actually equals to F. And this is, of course, our standard finite element system equation that we have seen so many times before. And we've seen just now that we can also find for our linear elasticity problems. Okay, now as before, this is the global equation, and whenever we're solving a problem or a finite element problem, we have to solve the global equation. But what we can do is that we can define our stiffness matrix and our right hand side vector element wise, that is Ke. I'm going to change this, sorry, to represent it as a small Ke and Fe, where each of these stiffness matrix and force vectors are being calculated for each element, and then we assemble them into the global equation before solving it, right? So all of this we are completely familiar with, I hope. So let's move on. So now comes what is actually different. As always, we've seen that every time we essentially we end up converting our various different problems into this equation, and the only thing that ends up changing is what is contained within the K and what is contained within the F. So for example, here we have K, which is BTDB, but what is B, what is D, what is B? That's the question basically. So for that, we need to actually look at the particular problem. So in this case, as you recall, our essential variable is our displacement. Now remember that our displacement is a vector, which means that it has two components, ux and uy. So every time we're looking at, let's say in our domain, we are looking at a triangular mesh, let's say, then for each node we will have a, let's say this node, I'm somewhere in the body, I will have a ux and I will have a uy for each node. That means that I have 2 degrees of freedom per node, right? Because my essential variable is a vector and I'm looking at a 2D problem. So I can write out my nodal displacement vector, as you all recall, our AE vector, using these 2 degrees of freedom for each node, such that what I do is that I write down first my x displacement for my first node, then my y displacement for my first node, and then I write down so this is basically the terms from one node. Then I write down my x displacement from my second node and y displacement from my second node. So this is my degrees of freedom from my second node, and so on until I get to my however many total number of nodes I have in it. And finally, this is being written as a transpose because AE, as you all know, we tend to write using a column vector notation. Okay, so using these nodal displacements, I can of course interpolate and I can find my displacements within any point in the domain. So I could find it within this element at somewhere right here. So in order to do that, you recall that we tend to use our nodal degrees of freedom for the interpolation. So if I want to find my ux at any point in the element, then I will find my shape functions n1, n2, and n however many nodes I have at that point xy and multiply those shape functions by their respective degree of freedom. So n1 being multiplied by ux1, n2 being multiplied by ux2. Please note that because I'm finding ux, then I'm only using my x displacements for each of the nodes. Okay, so only ux1 and ux2 and so on. Okay, but if I want to find my y displacement at any point in the element, then I will be using my y nodal degrees of freedom. So uy1, uy2 and so on. So I can write this down more compactly by representing my shape functions also in matrix format. But in this case, the matrix that I need to introduce is actually something like this, where I have n1. It has two rows. That's what's important from our previous examples that we've looked at. So it has two rows, and this time I have n1 0 0 n1 again right here, and then n2 0 0 n2. So it's a little bit different from our previous cases, and only when we write down our shape function matrix in this sort of format can we use our standard multiplication of n multiplied by a. Sorry, this should also be e and e. So n multiplied by a, because a has x, y, x, y. Hence why I need this n1 0, n2 0. Please multiply these two, ne and ae, to see that it actually does turn out that you get u as a vector of ux and uy. Please perform this matrix multiplication to see that this is actually what happens. Right, so we've got our displacement variable in terms of our shape functions and our nodal degrees of freedom. Now we can convert, now that we know what our displacements are, then we can find our strains, of course, because we know that our strain is just the del S being multiplied by U. So substituting in what we have for U, I get this expression right here, and I've already called this derivative as my B matrix, where now let's see what is inside my B matrix. Let's expand that out. So B is, as we've just said, it's del S times NE. So del S was this one. Go back to the slide number 2 for this lecture to find this. And then N we've just written down in the last slide is this one. So if I multiply these two out, then I get that my B matrix this time is something like so. So it has these new zero terms popping in, and also note that it has actually it's 3 by something rank. Okay, why is it 3 by something? Because recall that my epsilon is 3 by 1. Okay, so in order to get this 3 by 1, I need a B matrix which is actually 3 multiplied by what was AE, that was what was it? It was, yes, it was n node by 1. That was the rank for AE. Whereas for BE, then I have 3 by n node, the number of nodes that I have. Perfect. Oh no, it's not 3 by n node. This is 2 times n node, because we have 2 degrees of freedom. I apologize for this. And this one is 3 times 2 n node again. Okay, so these 2 n nodes, of course, if you're doing matrix multiplication, then we get a 3 by 1 strain vector. Sorry. Right. Again, just do this multiplication yourself to so that it makes sense to you. If I keep saying this, it will not. Honestly, the only way to figure this out completely is to do to look at these matrix multiplications yourself. Okay, so let's look at our 3-noded triangular element as just one example of what these A and N and B matrices would look like. So remember, if I have a three-noded triangular element, I have something like this. So 1, 2, 3, I'm just giving them random names. Then for each node, I have 2 degrees of freedom. That is, I have the x displacement for node 1 and the y displacement. So that my A vector, the nodal displacements, becomes ux1, uy1. So displacements of node 1, then ux2, uy2, the displacements of node 2, and then finally ux3 and uy3, that is the displacements of node 3, all written in column vector format. And my displacement variable then is, of course, this A being multiplied by the n matrix, where if I have just 3 nodes, then that is n1, 0, 0, n1, and then n2, 0, 0, n2, and so on, right? And if I multiply these two, yes, indeed, I do then get ux and uy, the expressions for ux and uy, right? What happens, what about the B matrix? So the strain, of course, in the element is given in terms of the B matrix, so B multiplied by A. So here the B matrix, you know that I had the expression right here, except that it would just be 3 times, how many nodes? 3 nodes, 3 multiplied by 2, so 3 by 6 B matrix, that's what it should be. So just substituting in the derivatives for my linear triangular element, I get this expression for BE. Note that these are the derivatives. So this would be, what is this? This is del n1 with respect to del x, which we have already looked at in our lecture when we had considered 2D discretization using the three-noded triangular element. And this is, what is this? This is del n1 with respect to del y. Okay? And similarly, del n2 with respect to del x, del n2 with respect to del y, and so on. Yes. Now let's just do a sanity check. Indeed, as we had just seen, this is a rank of 3 by how many? It should be 2 times the number of nodes, because each node has 2 degrees of freedom. So 1, 2, 3, 4, 5, 6. So indeed 3 by 6 matrix for our three-noded triangular element, right? Now notice that this B matrix is again just in terms of the nodal positions. So y2, y3 are just the nodal coordinates, nodal y coordinates, and so on. So this means that this B matrix is actually a constant. And if it is a constant, then if we want to find our stiffness matrix, which of course involved an integration, then if we are using a homogeneous material, homogeneous uniform material, then this B matrix is a constant and the D matrix is also a constant. So we can take all of that outside our integral, such that I then just have the integral of the domain. Now in 2D, we've already seen that this is, of course, just the area of the element. So it's very easy for us to find the stiffness matrix in this particular case of the three-noded triangular element, because it's just this straightforward multiplication of BDBA. That's it, right? We've already done the example of this in our heat conductance problem. Okay, just yes, one last comment on our three-noded triangular element, which is that if my B matrix is a constant, and A is the nodal degrees of freedom, those are constant, then that means that my strain in the element is constant. And if the strain is constant, then that means the stress is constant. Why? Because I know that sigma is equals to D times epsilon. So if B is constant, then the strain is constant, and if strain is constant, then the stress is constant, such that this particular three-noded triangular element is very commonly referred to as the constant strain element, such that if I am to plot a contour plot, let's say of a particular problem, so this is the problem in which this is a 3D problem, so these aren't actually triangular elements, but these are constant strain elements. So if I plot my stresses, let's say, if the strain is constant, the stress is constant, then I can see that one entire element of mine has the same color. One entire element has the same color because it has, over all of that element, it just has the same value of stress. Okay, similarly, another example, I have my triangular constant strain triangular elements in here. So the entire element is one color, red here, yellow here, green here. But if I look at some quadrilateral elements somewhere right here, then I can see that the stress or the strain is changing within the element. Okay, so just pointing that out, that if my B matrix is constant, then I will end up getting a constant strain element, right? Just to hone on this even more, we have discussed multiple times previously that if I'm looking at, let's say, my 3-noded triangular element, then I know that my shape functions are what? My shape functions are linear, right? If my shape functions are linear, then I know my displacement, of course, is interpolated using the shape functions, n multiplied by a. All of these are vectors and tensors or matrices, however you want to call it. So if I do plot my displacement, let's say I'm going to plot my ux variable. Note that I can only plot one at one time, so either ux or uy over some element boundaries. So these are my element boundaries. Maybe I was going through a line like this or something. I've got a line profile. Then my linear shape functions will lead to a linearly interpolating displacement profile, where the displacement profile, the essential variable, will be continuous over the boundaries. That is, these are C0 continuous elements. And even I now also know, even if I use which ones? Quadrilateral elements, then even then these will be the essential variable will be continuous, but I have to use isoparametric mapping for that. Now let's look at strain. So if I have strain which is B multiplied by A, again matrices and vectors, then plotting one of the strain terms. So let's say I'm plotting EXX. Note that there are two other ones. There is also EYY and EXY in it. Again against X. Again for these same elements. Then I know that I will get derivatives of those shape functions which are constants. So I can see actually even just from my UX graph that here I have a constant value for the strain in this element, and then in this element I will have a different constant value of the strain, and there is a discontinuity or a jump over the element boundaries, right? So that's basically all that I was saying in these slides right here too, that 3-noded triangular element, of course, is a linear triangular element, and hence why it has a linear distribution of displacement, but a constant strain within them, and hence why they're known as constant strain elements. Right, so that's the end of this week's lecture. So we'll discuss this on Thursday. I hope, I'm sorry for being a bit late. I hope it's not too difficult or too long to figure out. Right, okay. Office.